Welcome to UGC lecture series. We are today going to discuss the third episode of organic nitrogen compounds. In the earlier two episodes of organic nitrogen compounds, we have discussed aliphatic nitrogen compounds, and in which we have discussed their classification and their methods of preparation. We have also discussed various reactions given by aliphatic nitro compounds. Nitro compounds are very useful in organic chemistry because they are used as very good solvents and used as precursor for many synthetic reactions. In today's episode, we are going to introduce nitroarenes. We will discuss the methods of preparation of nitroarenes from diazonium salt and by direct nitration. We will discuss the reactions of nitrobenzene, in which we will discuss electrophilic substitution reaction like nitration, sulphonation, chlorination, etc. We will discuss nucleophilic substitution reaction. We will discuss nucleophilic addition reaction. We will also discuss the reduction of nitrobenzene in acidic, neutral and alkaline medium. Lastly, we will discuss the electrolytic reduction and selective reduction shown by nitrobenzene. In the introduction of nitroarenes, actually nitroarenes are aromatic nitro compounds. Nitro group is directly attached to benzene ring. They are named by prefixing nitro to the name of arene to which nitro group is substituted. Like in this case, you can see that nitro group is attached to benzene, and that is why the name of the molecule is nitrobenzene. Here the nitro group is attached to toluene. So, it is orthomethyl nitrobenzene is the name of this molecule. Here the two nitro groups are at meta position or at 1,3 position with respect to each other, and that is why the name of the molecule is 1,3-dinitrobenzene. Here position 4 or at para position we have a hydroxy group, and since hydroxy group takes priority over nitro group, the name of the molecule is 4-nitrophenol. We will now discuss the method of preparation of nitroarenes from diazonium salts. Diazonium salts, when treated with nitrous acid in presence of cuprous oxide, form nitro compound. This diazonium chloride, when treated with cuprous oxide, is forming nitro group over here. So, we get here 4-nitrotoluene. Direct nitration of aromatic compounds also produces nitroarenes. For example, nitrobenzene can be prepared by the reaction of benzene with a mixture of concentrated nitric acid and concentrated sulfuric acid. The mixture of nitric acid and sulfuric acid is also known as nitrating mixture. Here you can see that this is benzene reacting with nitric acid and concentrated sulfuric acid at high temperature, formation of nitrobenzene takes place. In case of toluene, when it is treated with the same nitrating mixture, we get orthonitrotoluene and para-nitrotoluene. The mechanism of nitration of benzene involves 3 steps. In the first step, there is reaction between nitric acid and sulfuric acid. This is an acid base reaction where protonation of hydroxy group of nitric acid provides a better leaving group like water. Now, the question arises why protonation of hydroxy group of nitric acid is taking place. Here you can see that the nitric acid is a weaker acid compared to sulfuric acid. That is why in presence of strong sulfuric acid, nitric acid behaves like base and there is formation of or there is protonation at this oxygen followed by removal of water and formation of nitronium ion, which serves as electrophile in this reaction. In the second step, the electrophile is attacked by the pi electron cloud of benzene ring, and in this step the aromaticity of benzene ring is destroyed. This is taken as rate determining step. You can see here this is benzene ring, pi electron of benzene ring or pi electron cloud of benzene ring is attacking the electrophile, and thereupon there is formation of this carbocation, and the aromatic character or aromaticity of benzene is destroyed, and that is why this is a slow step and this is also the rate determining step in nitration. In the third step, water functions as base to remove proton from sp3 hybridized carbon bearing the nitro group and restore the aromatic character of benzene ring. This is a fast step. You can see here that this hydrogen attached to sp3 hybridized carbon is removed by base water and there is formation of nitrobenzene. Now we will discuss the chemical reactions of nitrobenzene. See, nitro group is an electron withdrawing group, and since it is electron withdrawing in nature, it deactivates the benzene ring due to negative resonance effect and negative inductive effect. It withdraws electron from the ring or away from the ring and makes the electrophilic substitution difficult. Further, a partial positive charge develops on the ortho and para positions of the nitrobenzene, making it a meta-directing group. You can see here the development of positive charge deactivates the ring for electrophilic substitution. See, in these structures, resonating structures, you can see that this is nitrobenzene and there is development of positive charge here on ortho position, para position and then on another ortho position, making the benzene ring electron deficient. As a result, the electrophilic attack by the ring becomes difficult. Secondly, since the two meta position here and here, they do not develop positive charge during this resonating structures. So, even if in drastic conditions, if electrophilic substitution takes place on nitrobenzene, it takes place on meta position, and that is why we also say that nitrobenzene deactivates for electrophilic substitution reaction and at the same time it is a meta directing group. We will now discuss the mechanism of electrophilic substitution reaction. The nitro group directs the incoming group at the meta position. Why? The question arises that why it is directing the incoming electrophile at meta position. In the earlier slide, we have seen that during resonance structures, the positive charge develops on the two ortho positions and one para position with respect to nitro group, whereas the two meta positions are unaffected. As a result, electrophile or electron deficient moiety chooses to come over meta positions, and that is why the nitrobenzene is a meta directing, or nitro group in nitrobenzene is a meta directing group. Drastic reaction conditions are required for electrophilic substitution. Again, the answer lies in this resonance structure. You can see that the ring develops partial positive charge because of electron withdrawal by nitro group. As a result, the electrophilic substitution become difficult. Now we will discuss the nitration in nitrobenzene. Nitration is carried out by the reaction of nitrobenzene with a mixture of concentrated nitric acid and concentrated sulfuric acid, which is also known as nitrating mixture. When nitrobenzene reacts with nitrating mixture, it forms meta-dinitrobenzene. As we have already discussed, nitro group is meta directing, so the next electrophile comes at meta position. In case of sulphonation, this sulphonation is carried out by reacting nitrobenzene with a mixture of concentrated sulfuric acid and sulfur trioxide, which is also known as sulphonating mixture. Here again, the sulfonic acid group comes at meta position with respect to nitro group. In the mechanism of sulphonation, the electrophile SO3H is generated by the abstraction of proton from the sulfuric acid. There is formation of SO3H, the electrophile. The rest of the steps in sulphonation are same as they were in case of nitration. In case of chlorination, this chlorination is carried out by reacting nitrobenzene with chlorine in presence of fluorous acid like aluminium chloride or iron chloride. The chloro group substitutes at meta position with respect to nitro group. In case of bromination, bromine reacts with Lewis acid ferric bromide and forms a better electrophile as compared to Cl+. Now we will discuss Friedel Craft's reaction in nitrobenzene. The presence of nitro group in benzene nucleus deactivates it and reduces the electron density appreciably at ortho and para positions due to resonance effect, which we have already discussed earlier. Now, because of this, the compounds having deactivating and meta-directing groups do not undergo Friedel Craft reaction, and hence nitro compound do not show this reaction. On the contrary, the nitrobenzene is used as solvent in Friedel Craft reaction. The reason is it is capable to dissolve aluminum chloride by forming a coordination complex, and also because of the inertness towards Friedel Craft's reaction. Friedel Craft acylation of nitrobenzene does not take place under any conditions. However, the presence of a second strongly activating substituent group permits acylation. The site of reaction is that favored by both substituents. We will discuss it with the help of this example. Here in this benzene ring we have a nitro group which is electron withdrawing, and we have a methoxy group which is electron releasing. Now, when acyl chloride or acid chloride is treated upon with this ortho nitroanisole in presence of Lewis acid aluminum chloride, the acyl group CH3CO group goes to para position with respect to methoxy group and meta position with respect to nitro group. If you remember, we have just now told you that nitro group is meta directing. So, the meta position with respect to nitro group is comparatively electron rich, and in case of methoxy group, since it is electron releasing group, it increases electron density at ortho and para position. That is why this para position is reinforced because of the presence of electron releasing methoxy group and electron withdrawing nitro group. As a result, Friedel Craft acylation takes place at this position. We will now discuss aromatic nucleophilic substitution reactions in nitrobenzene. Nitrobenzene, when fused with potassium hydroxide, forms a mixture of potassium salt of orthonitrophenol and paranitrophenol, which on acidification form orthonitrophenol and paranitrophenol. Here you can see that this is nitrobenzene. When it is fused with potassium hydroxide, orthonitrophenol is formed and paranitrophenol is formed. We will now discuss nucleophilic substitution, where the replacement of halogen group located at ortho and or para position with respect to nitro group takes place. See this example. The nitro group is present with respect to chloro group at para position, and that is why here the reaction take place and this chlorine is replaced by a hydroxy group. See what happens when the nitro group is present at the ortho or para position, not at meta position. With respect to halogen atom in the benzene ring, it greatly activates the halogens towards nucleophilic substitution reaction. Moreover, greater the number of such activating group, greater is the reactivity of haloarenes towards nucleophilic substitution reaction. 2,4-dinitrochlorobenzene undergoes nucleophilic substitution under milder conditions compared to 4-nitrochlorobenzene, as the latter contains only one electron withdrawing nitro group. The substitution becomes easier when an increase in number of electron withdrawing nitro groups takes place. Like for example, here you can see with respect to this chloro we have 2 nitro groups. So, 2 electron withdrawing groups, that is why this carbon chlorine bond becomes a weaker bond and very easily it is replaced by a hydroxy group. Here in this case you can see we have 3 nitro groups and they undergo this substitution reaction. This 2,4,6-trinitrochlorobenzene undergoes nucleophilic substitution much faster as compared to 2,4-dinitrochlorobenzene or paranitrochlorobenzene, because of the electron withdrawal by 3 nitro group facilitates this substitution reaction. As seen, the substitution becomes easier with an increase in number of electron withdrawing nitro groups. Also note that the vacant ortho and para positions do not undergo nucleophilic substitution. You can see here that these positions, even though they are vacant, they do not undergo nucleophilic substitution. This is because even though ortho and para positions are electron deficient, the halogen is a better leaving group than hydrogen atom, because if substitution will take place at this, then the removal of hydrogen will have to take place. And if you will look at the leaving nature of hydrogen and chlorine, chlorine is much better leaving group than hydrogen. Now we will discuss the mechanism of nucleophilic aromatic substitution, which is also represented as SNAR, substitution nucleophilic aromatic, and this involves two steps. First step is addition and second step is elimination. The experimental evidence indicate that it is a two-step mechanism, often referred to as addition elimination mechanism. In the addition step, the reaction begins with the attack of nucleophile on the ring carbon bearing the leaving group, that is halogen. This produces an anionic intermediate known as Meisner-Heimer complex, which is resonance stabilized. Look at this molecule. We have a leaving group, or you can say in the earlier examples we had chlorine here. Nucleophile attacks this carbon and addition takes place at this position, followed by removal of this leaving group. These are the resonance structure of anionic intermediate which is formed by the attack of nucleophile on the carbon having leaving group. In the second step, that is elimination step, the ring undergoes re-aromatization with the loss of leaving group. In the first step, in which the ring loses its aromatic stabilization and anion is produced, is slow and rate determining step. The driving force for the addition elimination reaction is the anionic intermediate formed as a result of addition of nucleophile. Loss of leaving group in the second step, which provides aromatic stabilization to the product. Here you can see the order of reactivity towards addition elimination reaction. Here you can see this is the leaving group in the 3 molecules, and if we have a group at ortho position, if we had 2 groups at ortho and para position, or if we have 3 groups here, the order of reactivity towards addition elimination reaction follows this order. That is, if we have 3 electron withdrawing group, like in case of 2,4,6 trinitrochlorobenzene, the reaction was fastest, then in 2,4-dinitrochlorobenzene, and then in the 2-nitrochlorobenzene. We will now discuss the reactions of alkyl groups located at ortho position or para position, or ortho and para position both with respect to nitro group. The presence of nitro group at ortho or para position with respect to alkyl group alters the properties of these alkyl groups significantly. Normally, the hydrogen atom of alkyl group attached to benzene ring is not acidic or active in nature, and thus does not participate in condensation reaction with aldehydes and ketones. If however, nitro group is present at ortho position or at both ortho and para position with respect to alkyl group, then it alters the properties of alkyl group. Here you can see that this is the hydrogen atom attached to the carbon, which is directly attached to nitrobenzene. This actually is para-nitrotoluene. Now, if there is no nitro group, then the hydrogen here is not active or acidic in nature, but since the nitro group is electron withdrawing in nature, it withdraws electron towards itself. As a result, carbon hydrogen bond of methyl group becomes acidic in nature. As a result, this hydrogen can be released or can be taken out with the help of base, and it generates a carbanion here. This carbanion then can undergo condensation with benzaldehyde or other aldehyde or ketones. For example, para-nitrotoluene reacts with benzaldehyde in presence of base like sodium ethoxide and undergoes nucleophilic addition reaction followed by dehydration to form para-nitrostilbene. Here this is para-nitrotoluene. It is reacting upon with benzaldehyde in presence of sodium ethoxide to generate this para-nitrostilbene. Nitro group is firmly linked to the aromatic nucleus and is not normally displaced by other groups. However, in case of polynitro compounds having nitro group at ortho or para position with respect to each other, then one of the nitro group is substituted by nucleophiles such as OH or NH2. As in this case, you can see this is para-dinitrobenzene. When it is treated upon with alcoholic sodamide and heated, then there is one of the nitro group is replaced by amino group. Here the one of the nitro group is replaced by hydroxy group when the para-dinitrobenzene is treated upon with alcoholic KOH followed by acid hydrolysis. We will now discuss the reduction of nitrobenzene. Nitrobenzene undergoes reduction, different kind of reduction under different reaction conditions, and during the reduction these different kind of products are formed. That is, if we are starting with nitrobenzene, it is first reduced to nitrosobenzene, then it is reduced to phenyl hydroxylamine and finally to aniline. These are the different stages of reduction of nitrobenzene, and in presence of different reagents, reducing agents, different stages are achieved. First of all, we will discuss reduction of nitrobenzene in acidic medium. When metals and acid, metals like tin and zinc and acid like HCl or titanium trichloride are treated with nitrobenzene, they form aniline, and this type of reduction is called reduction of nitrobenzene in acidic medium. When the nitrobenzene is reduced in neutral medium, two different kind of reagents can be used. With iron and steam, the nitro group is reduced to nitroso group and there is formation of nitrosobenzene. On the other hand, upon reduction with zinc or tin in presence of ammonium chloride or calcium chloride in neutral medium, nitrobenzene is reduced to phenyl hydroxylamine. These phenyl hydroxylamines are reducing agents and they reduce tolerance reagent to metallic silver, which forms silver mirror on the glassware walls in which the reaction is performed. The reaction is used as a test for nitro group and is known as Mulliken's Barker test. The test is based on the fact that nitro group is reduced by reduced to hydroxylamino group. When reduced in neutral medium, the hydroxylamino group then reduces ammoniacal silver nitrate, which is the tolerance reagent, to metallic silver, and this metallic silver deposits on the wall of test tube in which the test is performed. The reduction of nitrobenzene performed with zinc in presence of ammonium chloride makes this Mulliken's Barker test. Here you can see this is nitrobenzene forms phenyl hydroxylamine. This phenyl hydroxylamine is treated upon with tolerance reagent and there is formation of silver precipitates on the walls of the test tube. We will now discuss the reduction of nitrobenzene in alkaline medium. In alkaline medium, the nitrobenzene is first reduced to nitrosobenzene and then it is reduced to phenyl hydroxylamine. These react with each other, that is the nitrosobenzene and phenyl hydroxylamine react with each other in alkaline medium to first form azooxybenzene and then they form azobenzene and finally hydrazobenzene is formed. Here you can see this is the nitrobenzene which upon reduction has formed phenyl hydroxylamine and nitrosobenzene. This is nitrosobenzene and this is phenyl hydroxylamine. They upon further reduction have formed azooxybenzene, azobenzene and hydrazobenzene. The end product depend on the nature of reducing agent. When the reduction of nitrobenzene by methanolic sodium methoxide is carried out, then it forms azooxybenzene. When nitrobenzene is reduced with alkaline sodium stannite or zinc and methanolic sodium hydroxide, it forms azobenzene. And when it is reduced with zinc dust and potassium hydroxide, then nitrobenzene is reduced to hydrazobenzene. We will now discuss the electrolytic reduction on nitrobenzene. Electrolytic reduction of nitrobenzene in strongly acidic solution first forms phenyl hydroxylamine, which in acidic solution rearranges by the migration of hydroxy group to para position and forms para aminophenol. Here you can see this is nitrobenzene. Upon electrolytic reduction, it has formed phenyl hydroxylamine, and the OH group from the hydroxylamino group has migrated to the para position of benzene ring, thereby generating para aminophenol. When electrolytic reduction of nitrobenzene is carried out in strongly alkaline conditions, first hydrazobenzene is formed, which rearranges to form benzidine used in the formation of azo dye. This rearrangement of hydrazobenzene to benzidine is called benzidine rearrangement, and the reaction involves the cleavage of nitrogen-nitrogen bond and formation of carbon-carbon bond. Here you can see this is nitrobenzene. This forms hydrazobenzene upon electrolytic reduction, followed by breaking of this nitrogen-nitrogen bond and then formation of this carbon-carbon bond. So, electrolytic reduction followed by benzidine rearrangement produces benzidine. We will now discuss selective reduction of nitrobenzene. In the presence of other reducible groups like vinyl or aldehyde group on the ring, the nitro group may be selectively reduced to amino group using alkaline ferrous sulphate. In this molecule you can see it has a vinyl group here at ortho position to nitro group. When we undergo reduction with alkaline ferrous sulphate, this carbon-carbon double bond or vinylic group is not affected, only nitro group is reduced to NH2, and that is why this reduction is called selective reduction. Here in this case the nitro group is present on benzaldehyde, or in this molecule we have an aldehyde group which also has a reducible carbonyl group and a nitro group which can also be reduced. But when the reduction is carried out with alkaline ferrous sulphate, only nitro group is reduced, leaving behind the aldehyde group unreduced. We will now discuss the reduction of nitro group when we have two nitro groups at meta position with respect to each other. In this particular case, when the molecule is treated with ammonium sulphide or sodium polysulphide, the one of the nitro group is reduced selectively, leaving behind another nitro group unreduced. So, this is also an example of selective reduction of nitro group. Here is the reduction of nitro group with metal hydrides like sodium borohydride or lithium aluminium hydride. Lithium aluminium hydride reduces nitro group to azobenzene, while sodium borohydride reduces it to aniline. Here this is nitrobenzene. When treated with sodium borohydride produces aniline, when treated with lithium aluminium hydride produces azobenzene. To summarize now today's lecture, we have discussed the introduction of nitroarenes. We have also discussed method of preparation of nitroarenes, which can be prepared either from diazonium salts or by the direct nitration of aromatic compounds. We have discussed various reactions given by nitrobenzene. Under this category, we have discussed electrophilic substitution reactions in detail. We have discussed nitration, sulphonation, we have discussed chlorination, we have also discussed acylation reaction under extraordinary conditions. We have also discussed that nitrobenzene does not undergo Friedel Craft alkylation, but serves as a solvent for this reaction. We have then discussed nucleophilic substitution reaction in case of nitrobenzene. We have then discussed nucleophilic addition reaction, which take place in nitrobenzenes if the nitro group is present at ortho or para position with respect to the alkyl group in an benzene ring. Then we have discussed the reduction of nitrobenzene under different conditions, that is in acidic conditions, in neutral conditions and in alkaline medium also. After that we have discussed electrolytic reduction and selective reduction of nitrobenzenes. In the next episode of organic nitrogen compounds, we will discuss the amines. Amines are another class of nitrogen compound with a functional group NH2. If attached to an aliphatic ring, they are called aliphatic amines. If attached to aromatic ring, they are called aromatic amines. We will discuss in detail about amines in the next lecture. Thank you very much.